As you work more with hardware, you're going to find that you'll need to understand a lot more about how computers actually work at the foundational levels. Well, inside of every computer is hundreds of thousands of transistors. Transistors are small little devices placed on semiconductive silicon that let electricity either through or not. It's a simple switch. And your computer is made up of so many of these transistors that fire all at once that it can break down all of the things you're asking it to do into a simple on or off. Well, that on and off is typically represented by what we might call binary. Binary is a base 2 system of representing numbers using only two symbols, 1 or 0. In computer world, 1 typically represents that we let electricity through the transistor, and 0 represents that we stopped it. The two states perfectly represented in symbol form. Well, you can represent everything in the known world using binary. You just have to use a lot of 1s and 0s to do it. So how does that translate? How do you have a system of counting with only two symbols? Well, if you think about our typical counting system, which is called decimal, well, that has 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then, to represent the actual number 10, you combine two of these symbols together, the 1 and the 0, and you continue adding symbols as you have higher or more complex numbers. Well, binary works the same way. You just have to add on more symbols pretty rapidly. Here's how you would count in binary. The binary for 0, like the decimal for 0, is 0. But let's look at the decimal for 12. How do you actually represent 12? Well, we know that if it's over the number 10, we need to add a new place or digit to our representation. So then we have the 0 place or the 1s place, and then the 10s place. The way that you would calculate 12 is you would take the number 1 to the left and multiply it by the base of 10 raised to the location of this digit in the index, which is 1. So 1 times 10 to the 1 is 10. And then you add that with the 1s place, which is the value of 2 multiplied by the base of 10 raised to the power of, again, that digit, which in the 1s place is 0. So how would you do this in binary? Well, the binary for 12 is 1100. You need 4 digits in order to do this. And you start counting at 0 and work your way up to 3, and you multiply it by the base of 2 raised to that power, multiplied by that actual value, either the 1 or the 0, and then you add it all up together. So you can see here that the system for calculating numbers in binary is exactly the same as the system for calculating numbers in decimal, but it just takes a lot more symbols. So you can see how you would sort of exponentially grow the number of 1s and 0s. However, computers are really, really fast and contain a lot of transistors. So this is how we break everything down. So why do we care about binary? Well, if the 1 or the 0 represents a transistor turning on and off, it also typically represents the smallest unit of memory within the computer. Either it's storing a 0 or a 1. But that's in fact such a small amount of information that we never really talk about memory in the terms of bits. We almost always talk about it in terms of bytes, which is a collection of 8 bits together, which, if you think about our base 2 system, 2 raised to the 8 gives you up to 265 different values that that byte can represent. However, again, you probably still don't talk about it in context of bytes. You've probably heard the terms kilobyte, megabyte, gigabyte, things like that. That is respectively 1,000, a million, or a billion bytes all stored together, which, if you think about them as 256 different values all sort of exponentially added up, now you can actually do some really cool things, all breaking down eventually into binary. The other number system you might see throughout this course is called hexadecimal. So if decimal is a base 10 system and binary is a base 2 system, hexadecimal is a base 16 system, which means it has 16 symbols to represent information. But we only know of 10 numerical symbols, so where do the other symbols come from? Well, we borrow the Roman characters A, B, C, D, E, F to represent the numbers 10, 11, 12, 13, 14, 15. So in hexadecimal, you start adding digits after 15 because you start counting at 0. So the number 10 in hexadecimal, maybe it looks like 10 in decimal, but it's actually 16 in hex. So why do we care about hex? Well, if we only ever talk about memory in the context of 8 bits, which is 1 byte, well, you only need 2 hexadecimal digits to represent 1 byte of information, saving yourself even more memory. So if you actually print out the memory location of any of your variables in C, you're going to get a series of letters and numbers. That is a hexadecimal address, and it saves your computer memory in order to save the location of all those things, since it only needs 2 digits to represent a single bit. You don't have to be able to count in binary to be able to program embedded systems, but the more that you understand about how computers work at a foundational level, it'll be easier for you to understand how much you can ask of your computers and what they can really do for you.